Hey everyone, welcome back and let's write some more neat code today. So today let's solve the problem largest color value in a directed graph. Now while this is a hard problem, whether you're a beginner or somebody who's been grinding a lot, I'm going to show you some steps you can take to solve difficult problems like these. And the most important thing, especially with this problem, is just reading the problem carefully. I'm going to go through the prompt at least in a more simplified way because sometimes they try to confuse you with the prompt. But the most important thing about this problem, in my opinion, is all the way at the bottom of the description, which I'm not showing here, but we're given a string of colors. Basically, we're given a graph here. Every single node has some color associated with it. Now, this is red, this is blue, this is purple. That doesn't really matter because each color is going to be represented with a lowercase character. That's right. Each color is going to be from lowercase a through z. That means that the number of colors is limited to 26. That's really one of the most important things about this problem. That's what you have to catch. But for the most part, this is like most graph problems. We're given a directed graph of n nodes in this case. N is not going to be a parameter, but we're also given a string called colors, which represents the color of every single node. So basically in that string, the 0th position might be lowercase a, that maps to this node, and the first position might be lowercase b, that maps to this node. So if we can just take the length of the colors array, that will give us the number of nodes, which is n in this case. We're also given the list of edges. They're directed. There's nothing special about this, but mainly we're going to use that to build our adjacency list because usually when you traverse a graph, you don't want to traverse it using the list of edges. The most common way that we traverse things is using an adjacency list, where we map every single node to its list of neighbors. So in this case, 0 has 2 neighbors that it can reach, 1 and 2. They also describe to us what a path in a graph is, as if we don't know that. I don't know if they are trying to confuse us here or they just assume that we're stupid, but yeah, a path is just a path in the graph. Like this is a path, meaning we go from 0 to 2 to 3 to 4. We obviously can't go in the reverse order because the edges are directed and they're only going one way in this case. Now take this path as an example. What's the most frequent color in this path? Well, let's say this is a blue. We have one blue, but we have 1, 2, 3 red nodes. So the most frequent color is red and the count of it is 3. So the only thing we're trying to do in this entire graph is find the path that maximizes the most frequent color. So in this entire graph, this is the path that maximizes the most frequent color, which is red, and the frequency is 3. And in this case, that's what we want to return. Not the color, not the length of the entire path or anything, but the frequency of the most frequent color, which in this case is 3. There's no path that we can make in this entire graph that will exceed that count. Now, it's possible that a graph could have a cycle. Like what if we have a graph that looks like this? Well, then we're just going to get stuck in an infinite loop. So they do tell us that in that case, we can just go ahead and return -1 because we can't really find a valid path in that case. So now we finally understand the problem, which I think is the hardest part. Now, I don't know about you, but anytime I encounter a graph problem, the first thing I try is the depth first search algorithm, DFS, because it's the most popular algorithm. It's the most common, so you definitely want to check, is that going to lead us to a solution? So let's try it out. How could we apply depth first search to this problem? Well, in the worst case, we might have to look at every single path. So how do we run DFS? Where do we even start? It's not like they give us a starting point. It's not like we can just start at node 0. How do we know we start here? Why not start over here? So I guess in the worst case, we'd have to run DFS on every single node. Isn't that going to be really inefficient? Because running DFS might cost us the entire size of the graph. So O of n, let's say, is the number of nodes. Well, technically it would be n plus m. M is the number of edges because we might have to traverse the entire graph. And how many times are we going to do this? Well, maybe times n because we have to run it on every single starting point. But is there something smarter that we can do here? Let's suppose I ran DFS starting from 3. I found out that starting from here, this is the only path that we can really make. So starting from 3, how many blue nodes were there along the path? Well, there was just a single blue node. How many red nodes were there? Well, there was just a single red node. So you're probably starting to get the idea if you have some experience with Leetcode problems where I'm going with this, but I'll continue for now. That was just the path starting at 3. Now, let's just say randomly we run DFS starting at 2. You might think now, this DFS in the worst case is now we might have to again traverse the entire graph, but 2 only has a single neighbor and it happens to be 3. So why should we now have to rerun DFS on this portion of the graph? We don't need to, we already have all that information stored over here. So when I'm asking the question starting at 2, what's the maximum frequency of blues that we can get? What's the maximum frequency of reds? And we also have a third color here, purple, so I'll just add that right over here. But it's obvious that I don't need to repeat all of this work. So what can I do instead? Well, I know that starting at 2, we do have a single red node, so maybe I can just put a 1 here for now. And then I go to my neighbor 3, I see it's already been visited. I'm not going to run DFS. I'm just going to look at row 3, which is going to tell me what's the max frequency of blues and reds. So what I'm going to do now is look at this position, blue. Now, so far, let's just say we have 0 because starting at 2, 2 does not have any blues. We're going to see that starting at 3, we can get a maximum of 1 blue. So since this value is greater than this value, we should take this value and move it over here. We can get rid of this, and now we have a 1 because we know going from 2, we can get to 3, and we know this path will have a single blue. So that means starting from 2, there is a path that maximizes the number of blues, and that path will lead us to a single blue. And we're just going to go column by column and do the exact same thing for every single color. So here, it's a little bit different though, because we know 2 actually was the color red. So here, we're not going to take the maximum of these 2 values. We would actually take this value and add it to the value over here. So I'm going to get rid of this and add 1 to it. So now we're going to have a 2 over here. And we would do that column by column. Here, they're just going to be 0, so we don't really need to do anything. But it's not entirely this simple, because it's possible that 2 actually could have had additional neighbors going in other directions as well. It doesn't in this case. This graph is pretty simple, but this could have been the case. So what would we have done in that case? Well, let's say another neighbor happened to be 4, like this neighbor over here is 4. So just to make it simple, we have a 4 here. There's some values here, X, Y, Z. We don't care what they are. But again, we would go row by row. We'd say, let's look at these. And since, remember, for every single node, we're trying to maximize this position. We're trying to find the maximum number of blues, the maximum number of reds. So what we would do as we go column by column, comparing these 2 values, we would take the maximum of both of them. The only edge case here is that on the source node, which is 2, for the column where the source node is the actual color, like in this case, this source node was red, here we would just want to add a +1. So we just have to keep track of that edge case. We wouldn't just, in this column, we wouldn't just take the maximum of these 2. We would have to kind of consider a +1. But that's the only edge case. Otherwise, this isn't super crazy. And you might think, well, for each iteration of the DFS, if we're having to do these operations, if we're having to go through this entire thing, isn't that going to lead us to a pretty inefficient solution? Not quite, because remember what I said at the beginning. The number of colors is bounded to lowercase a to lowercase c. It's bounded to 26 colors maximum. So it really isn't that bad. And since we're never having to repeatedly visit the same node twice, the overall time complexity of our DFS is just going to be the size of the graph, n plus m. Well, we do have a factor of 26, but that's a constant value. We don't really care about that. So this actually will lead us to the most optimal solution, at least in terms of big O time complexity. I will mention there is a solution that will get you a better runtime on Leetcode, but this still will give you the big O time complexity, which usually is the most important for interviews. So I think it's safe to stick with this simple approach, and we didn't need anything super fancy. All we needed was depth first search. I didn't mention though, there could be the possibility that we detect cycles, and I'll basically talk about how we can do that within the code. At a high level, as we visit nodes, like as we start at 0, we go to 2, we go to 3, we go to 4. If we ended up coming back to the same node, we'd want a way to track that. I'm going to do that using a visit hash set. Well, I think I'm going to call it something else because we're going to have visit to not repeatedly visit the same node twice, but we're also going to have another hash set. Maybe I'm going to call it path to tell us what are the nodes in the current path of our recursive DFS. Like what are the nodes on the call stack of this DFS. So now let's code this up. So I'm going to start with just building the adjacency list. This is not super complicated, so I'm just going to have that here. We're basically creating a hash map where the default value of the hash map will be a list / an array. We're going to go through every edge, and we're going to map the source node to the destination node. We're also going to have a depth first search, and what we want this DFS to do is, given some node as a parameter, we want it to return the max frequency of the most frequent color. So that's ultimately what we want this to do. Now, I'm not going to fill it in yet because I usually think it's better to see how we can use it before. So that's what I'm going to do. We know we're going to go through every single node and try to run a DFS starting from that node. Well, first of all, how many nodes do we have? Well, thankfully, we can get that by taking the length of the colors array. So then I can complete my for loop for I in range n, and then pass in that starting node into our DFS. Now, what we're trying to do is maximize the result. So I'm going to, well, first declare that variable. Result is initially, let's just say, is going to be set to 0. That's usually a good default value. And we want to maximize the result. So we're always going to take the maximum of the result of this DFS and the maximum of the result and set it equal to the result. Now, like I said, we are going to need to keep track of which nodes have already been visited so that we don't do repeated work. And we're also going to keep track of which nodes are in our current path of our current DFS, like which nodes have been pushed onto the call stack, because that will help us detect cycles. Well, it's required for us to detect cycles. So these are both going to be hash sets, so we can do that just like this. And this is kind of the complicated part. I didn't explicitly talk about it, but I kind of showed it with the picture. We are going to have a two-dimensional grid, which tells us the max count, where we are mapping the count, the node, and the color to the max frequency of that color starting from this node. So just like we talked about in the drawing explanation, now to actually initialize this 2D grid, well, I'm going to do it the pretty much Pythonic way. You can do it however you would like, but we know that every row is going to be the number of colors. So the row is going to be 26 because we could have up to 26 colors. So it's going to be an array with 26 zeros. That's how you can do it in Python. And how many rows are we going to have? Well, one for every single color. So I'm going to say for I in range n, which we calculated up here. So this is just a two-dimensional grid, pretty much with these dimensions, and this is going to be useful for us in our DFS. Now, lastly, I'm going to put our return result here. We are going to modify this. I'll mention that now, but I'm going to save it until we finish up our DFS, because remember, we want to return -1 if we detect a cycle. So we'll have to keep that in mind. But now let's go on to the DFS. There's a couple edge cases. If the node is already been visited, then we just want to return immediately. I'll just return 0 because it doesn't really matter. There's also the other edge case. If the node is in the current path, then we want to indicate that we've detected a cycle. So we have to return some special value here. We could do -1, but the reason I'm going to do something different, I'm going to do float infinity, basically like the maximum value that we can return. The reason I'm doing this is it makes our code a bit more concise. You can do it the -1 way, but you'll find that you need like a couple extra lines of code. Doing it this way, when we take the maximum, because that's ultimately what we're trying to do, we're trying to maximize this. If we ever return infinity from this DFS, we're going to take the maximum and then our result will be infinity. And once it's infinity, it can never become smaller than that. So then by the time we get to this return statement, we will be able to detect, is the value infinity? If it is, what we really want to return is -1. So I'm going to do exactly that. Return -1 if result is equal to float infinity. Else, return the real result, whatever it happens to be. It's probably 0 or some positive value, but it's not infinity. Now, one thing that you might not notice here is we kind of have a bug here, because every time we get a node that's not been visited and is not in the current path, what we're going to do then is add it to the visit hash set. So we're going to say this node has been visited and this node now is in the current path. So now if we visit that same node again, then we're going to end up executing one of these. But notice if the node is in the current path, it's also been visited. So if we get a node that's already been in the current path, what we'd want to do is return infinity to indicate we detected a cycle. But that would never happen because we would always execute this one first. So it's very important that you take this condition and have it before this condition. That's an easy way to have a bug, so definitely something to keep in mind. Now for the kind of interesting part, we want to take the count, the maximum frequency color starting at this node, and just set it. And for the color of this node, we want to set it equal to 1 because we know at the very least this node is some color, and we can find that color and map it to 1 initially. How do we get that color? Well, that's where our colors string comes in. We can take this node and map it to get the color of it. But remember, that string will return us a character. What we want is an index. So from lowercase a to z, we really want to map a to 0. We want to map b to 1. And we want to map z probably to 25. So how do we do this? Well, I'm going to do that like this. I'm going to basically call it the color index. And I'm going to get the ASCII value of that color, basically mapping that color to some integer and subtracting the ASCII value of lowercase a. So if the color of that node is lowercase a, this will evaluate to 0. If the color of that node is lowercase b, this will evaluate to 1. So pretty much what we were looking for. Then I can use this color index to use it as an index of this two-dimensional array. Now, finally, we want to start going through the neighbors of our current node. So we can get our adjacency list. That's what we built this for. And use the current node and get all of the neighbors of this node. So while I haven't done anything super crazy, you can see that this is quite a lot of code. It's a lot of things to keep track of. It's really easy to make a bug here. That's what makes this a hard problem in my opinion. But for every node, we just want to run a DFS on it. Now, the only edge case we have to worry about is what if it returns infinity? Because if it does, then we should probably just return infinity right away. And that's what we're going to do. We're going to detect the return value of this. Is it equal to float infinity? If it is, we're going to return float infinity. Now, I didn't store the return value in a variable because we actually don't need it in this case, because whatever the DFS did, the most important thing is that it populated our two-dimensional count array. So we don't need the return value, we just need the count array. So now I'm finally going to do the thing that I talked about where we go column by column. And how many columns do we have? 26, one for each color. So I'm going to say for C, which basically stands for color or column, whatever you think, whatever you prefer, I guess. But there's going to be 26 of them, so we're going to iterate 26 times. We want to take the maximum of the count for the current node, like the starting node, which was the parameter of this function, for the current color. So this will give us that count, and we want to maximize it with the neighbor. So the neighbor here with the same exact color. We want to find the maximum of these two values, and we want to assign it to this position, just like we talked about in the drawing explanation, because right now we're considering this node as the starting point. Now, the only edge case is, which again I mentioned in the drawing explanation, is when we get to the color, which is the same color as this color, like as the same color as the starting node here, in that case, we would want to add a +1. We want to add a +1 to the neighbor's path because the neighbor has not considered this node yet. So here we'd want to add a +1. What's the easiest way to do that? Well, in my opinion, to add like a ternary operator. So here what I'm going to do is say this is going to be 1 if C is equal to color index. Otherwise, it's going to be 0. That's the most readable way in my opinion. You can definitely try other things, but I prefer this because we don't need to create more and more variables, because the more variables you create, the more names you have to create. And in my opinion, what makes code confusing to read is bad names. And I'm pretty good at creating bad names, so I try to minimize that. Now this loop will find the maximum for every single color starting at this node. And then that's what we want to return. So starting at this node, we want to find the maximum frequency of any color. So we don't care which color, we just want to find the maximum. So this is an array. We can just take the maximum of it and return that. So then this method will do what we want it to do. The only thing that you don't want to forget about is when you add a node to the current path, right before you return, you want to clean up. You want to remove that same node from the current path. We can do that just like this. We don't need to remove that node from the visit hash set because we never want to visit the same node twice. We also don't want to add the same node to path twice, but it's important for us to pop because then we can actually detect cycles. So that is pretty much the entire code. It's quite a lot of it, so hopefully I don't have any bugs. Let's run the code to confirm. And as you can see, it does work. According to Leetcode's runtime, it's not super efficient, though the big O time complexity is definitely optimal. I can guarantee you that. There just happens to be other solutions to this problem that happen to get a better runtime on Leetcode, but I don't think that's super important. If this was helpful, please like and subscribe. If you're preparing for coding interviews, check out neetcode.io. It has a ton of free resources to help you prepare. Thanks for watching, and hopefully I'll see you pretty soon.